Hello out there. Today we're going to write another program in our favorite learning language, which is Golang. We will implement a simple little password tester. So as you can see here, I got a few passwords and I wrote a program to try to find and basically break these passwords. So here's a little text file where I just added a few passwords containing alphanumerical characters of length 5. And the idea is to write a simple Go program that tries to guess all these passwords in a reasonable amount of time. So as you can see here, when I run my program, it shows which kind of symbols are allowed in the password. We said these are alphanumeric symbols, so uppercase, lowercase letters, and digits. These are 62 symbols in total, and we pick 5 out of these. So these are my randomly chosen passwords from the file, and the program just tried out every possible combination until it finds a matching password and then prints how long it took and what the password is. And as you can see here, it took between a few milliseconds and seconds depending on the password. Since our approach is systematic, it will be similar on another run. And we will use this example today to improve our knowledge about programming and to introduce a few new concepts that I haven't addressed in earlier tutorials, like for example, recursion. All right, so without talking too much about the solution, let's start with a fresh project. As you can see here, I created a fresh folder and I'm just going to create a new main.go file. And I'm also going to create a new pv.txt file. This is where we are going to put our test passwords that we want to find out. Now a little disclaimer before we go on. This is not a real security safe program. This is just for learning and playing purposes. So please don't assume that this is safe for your real passwords. Please only use it with imaginary passwords for learning purposes. So I'm not going to give you any of my real passwords here, of course, because that would be unsafe. I will just enter a few alphanumeric characters here for learning purposes. So can have digits, uppercase or lowercase characters, and this is my example file. Let's say one more. Like this. All right, so we're going to write it for 5 symbols. And that will give us a good idea about how long it takes. So as you might already know, 5 symbols is pretty short. So usually it should be much longer, like 12 or more symbols. It used to be 8 upwards, but even 8 is a little bit short for today's computation powers. So let's go to our main program. As usual, we declare it to be in the main package. And for printing, we're going to import the FMT package. As usual, let's test our hello world. First, project setup. I'm going to save and use Gorun. You can, by the way, specify Gorun dot by now, and you don't have to specify main.go every file in the main package. I didn't find a mod file, so as usual we should initialize our Go module. And as always, I'm just going to use my GitHub path to this project, PV tester. Can be anything for your personal project. Now it says we should run go mod tidy, and that's about it. Let's see if go run works now, and it does. We get a hello world. Alright, so next we need to make sure that we read the test passwords from our txt file, because we have to test our guesses against the actual password that we want to guess. So, as we've already done in earlier tutorials, we can use the file operations. So, for example, os.open for opening a file for reading, pv.txt. As usual, we have to check for potential errors. So if error is not nil, we need to handle the error. And in our case, we can't really do much except for printing the error for debugging purposes. And then exit the program with an error code. So I'm going to call os.exit with code 1, because code 0 usually stands for termination with success, and a non-zero exit code for an error. Now we want to read every line from the file. We can use, I guess it's buff.io package to create a new scanner. It expects a reader. Please read a bit online or look at one of my earlier tutorials about these I/O functionalities. We're just going to use that here to read from the file. And then we get a scanner. We can look at the implementation. And then we can use that scanner to read line by line. So the default is to read line by line. So we don't have to configure any custom split function. But we have to check for a scan. So as long as scan returns true, we got new content from the file. As it says here in the documentation, it returns false and the scan stops. So at the end, let's say the scan stops, then we need to check for errors. So in case the scanner occurred any errors, then we should check that here. Now as we need this error handling code here again, we can extract it to a simple helper method. I'm going to call it check, and it receives an error and it will print error info and terminate the program in case something went wrong, and then we can reuse it here to avoid too much code duplication. Okay, so now we got the error handling, which is always important. We can say while scanner.scan returns true, we want to read a line. Now we we can either do this with returning a byte slice or returning text in form of a string. We are immediately going to use the string version here. Please note that the string is nothing else than a slice of bytes. So bytes are the fundamental storage unit of computers. They consist of 8 bits. It's just binary, so zeros and ones. And by interpreting these bytes in a specific encoding, we get displayable strings. So it's not that far apart, just that by not using the slice of bytes here, but immediately text, we get this as a string. So this is one line. And just to make sure we got this right, we're going to test this part by just printing the lines. So save and then run our program. And now it prints the content line by line. That's exactly what we want. Great. So we can remove the hello world. And to give you another idea about the distinction between bytes and text, we could also say that we want a byte slice, then that these would be bytes. And so to make it a bit more explicit, it would look like this. And line bytes. Of course, we can't directly print. Actually, we can. Let's try this. And here you can see byte values. So these are binary values that represent our symbols in the string. So basically the individual characters, depending on the encoding. So the encoding specifies how these binary byte values are translated to actual symbols that can be printed, for example, in a terminal, but also in a web browser or something else. So by default here in my editor, this is encoded as UTF-8. I can see it down here. There are many more encodings, but UTF-8 is a very popular and widespread encoding for holding all kinds of symbols. It's pretty well established and modern. So you don't have to worry much about, can this hold, for example, Asian characters or non-Western symbols. It can contain quite a lot of different symbols, almost anything. So this is a slice of bytes, and you need one or more bytes to represent a unicode code point, which is basically one symbol here, like a P or an 8, or it could be an non-Western character. And by using a conversion to string, you can write it like this. We tell Go to interpret these bytes as strings, which are, as it says here, conventionally representing UTF-8 encoded text. It could be a different encoding, then we would have write more code, but by default it is assumed to be UTF-8 encoded. And then you can see it's interpreting this as actual printable strings. So that is the relation between a byte slice and string. I hope that got a bit clear. In this case, one byte value is equal to one printable symbol, but if you use different symbols, maybe also like emojis and stuff like that, then it will usually take more than 1 byte, and these could be longer. So don't assume that it's a one-to-one relationship, but most of the time you don't really have to worry about it, because once we make it clear this is a string, this is pretty transparent for us. Now another interesting thing is we got bytes here, which is the encoded representation. We got string, which is the complete representation of the byte slice. There's also a type in Golang and other languages for handling individual symbols of the string. And in Golang, this is called a rune. So what we can do is we can loop over these bytes. I will use a range loop. And let's call this symbol. Or actually, yeah, it's a byte, so I'm going to call this just B for now. Range over line bytes. And then we're going to print it. And we're going to use the default format fv and pass a byte from the slice. So then afterwards, let's make a new line so we can actually distinguish these. Now, as you can see, we get the byte values like up here, just one by one, and there's no blank in there, so it's a bit hard to read, but we could write it like this, and then we basically got the same. But now we don't want the byte values, which is the encoded value, but we want to see the individual symbol here. And that is where runes come in. So we can say that we want to interpret these bytes as runes. And the placeholder for that is C, %C. And I'm going to convert this byte. Actually, it's not the byte because, as I said, multiple bytes can be required per symbol or per rune. So instead, we are going to say here that these bytes are a slice of runes. So it says cannot convert. So we basically have to use the string as an intermediate way. So let's say we got our string line here. And now we can range over the string. And that will give us the symbol, which is a rune. So as you can see here, it is automatically declared as a rune because a string consists of individual runes, which is just one character here, but it could also be an emoji or an Asian character, Indian symbol, Swedish symbol, whatever. So let's see how this looks like. And it looks like this. So since we got our blank here, you can see that it's printing and processing, basically looping over every individual rune in there. So that is pretty important for our password testing, because we need to process, guess, and test by individual symbols that make up a complete password string. So that brings me to the next topic. We need need to hold our red password somewhere, and for convenience, since we want to test it for matching guesses, we can just create a new type, and I'm going to call this password, and it will be based on a rune slice, because as we already know, a string consists of runes, so you can say that a slice of runes is a string. So let me note that here. And now we can say that what we read here is a password. So we can say pv int create a new password, which is our line. And then let's print that like this. And you can see we are actually back to printing the individual integer values. So that is because now we no longer say interpret this as a rune, but we interpret this as an individual printable symbol. But we said just print the runes, and runes are actually defined as an int 32. So let's add this here too. As an alias, something I also discussed in a previous video. So a rune is basically just a 32-bit, so 4-byte integer. So it can hold up to 4 bytes because a byte consists of 8-bit and 32 divided by 8 is 4. Can hold 4 bytes. All right. So a rune is a 4-byte integer. And when you create a slice of these 4-byte integers, aka runes, you get a string. So that is the basic composition of these types in Golang. And don't worry, it will make more sense when we implement our password testing. So now that we got this, we can also say we don't want to print the actual integer values, so the 4 bytes, but again we want to interpret this as printable symbols or characters, if you might say so. So we use the %c formatter. And now we're back to the printable, more human readable version. So these integer values, those runes, get interpreted as the actual symbols for printing. This is our slice, so that's why we get those square brackets. Okay. Now we have a representation for our passwords. Let's write a method for checking if we guessed right. So we write a method like this. We already learned that in a previous tutorial, and I'm going to call it matches. We pass another password, which is basically just a slice of runes, so guess. I'm going to call it guess. And we return a boolean true if it matches, false if it doesn't match. Initially, I'm going to return false, and actually let's write a small unit test for this functionality. So package main, we need to import the testing package, and we write a test function, test password matches. So let's create a password. And like this. And now we're going to call matches and give a guess, which is something else. Let's say that is something completely different. So it should return false. So if that returns true, we have to fail because it shouldn't. So here it says cannot use string as rune, but we can actually use a type conversion here. So next we're going to test it against maybe a password that is almost the same, but one character too short. Completely different guess. And we're going to use one that is too long, so we will add another character. And then we're going to just have one little difference in there. Let's say we have a lowercase here, but the rest, let's say we have an uppercase D, but the rest matches. It's this, so this is the original, and now too short, too long, and lowercase here. And then at the end, we test the correct, like this. So if that is not true, we expect it to be true, then we need to fail the test. So right now we just set return false, so it's basically a test-driven approach. Let's test this. And it says fail, expected true for correct guess. And of course we didn't implement the check yet. So let's quickly implement it. At first we should verify that the length is the same. So length of this password. If it doesn't match the length of our guess, we need to return false. Then, since we know the length is the same, we have to iterate and compare it symbol by symbol. So we define an index which starts at 0 and goes up until we reached the length of our password. So if these values at the same index are different, then we need to return false. So we can immediately exit with false. We don't have to check further characters, so that is a bit more efficient. And at the end, if we didn't exit with false earlier, we know they are the same. So let's see if it works. And it does, it passes. Yeah. So in case you wonder, there's no standard equal implementation for slices in Golang. There is one for arrays, and there is a helper function in the Bytes package if you want to compare byte slices. There's also a reflect package, which can be used for that, but since this is a bit efficiency and time critical for us, we won't be using it and implement the check ourselves. But it's not that hard to do, as you've seen, and you can also use a generic implementation if you want to reuse it for different types later. Okay, so now we can read our passwords from the text file. We can also hold them in this type, and we can check for a match. That is our basic fundament, as well as understanding what runes are to start with the actual password finding. So first we have to cover the general idea, and that is because we have to think about what our program actually has to do. So as an input, we give it a password, right? Or multiple passwords. We allow alphanumerical characters. So these are lowercase a to z, uppercase a to z, and the digits 0 to 9. In total, those are 62 symbols, 26 letters 2 times, and 10 digits. These are the distinct symbols in our password. We decided to test with a password length of 5. So that is for demonstration purposes. It is pretty short. So again, disclaimer here. When you use real-world passwords, make sure they are of sufficient size. That depends on the current recommendations and how strong the computing power has become. But at the time where I record this, it is recommended to use at least 12 characters and include uppercase, lowercase, and also consider digits and special characters to make password cracking harder, because we just want to do this for learning purposes here. So you may wonder how many possible distinct passwords there are, and there's a simple equation for that. You can just use the number of distinct symbols as a base and the length of your password as an exponent. So it's just exponential. In our case, 62 and an exponent of 5. So that means you multiply 62 with 62 with 62 with 62 with 62 5 times. And that is a quite big number. It's here, so 916 million. And if you extra, that is basically the total count of possible passwords you can create with these symbols. Note that symbols can repeat, so it would also include things like A is contained twice, or even all symbols are A. And it also respects the order. So For example, AAAB is different from BAAAA. But that gives us a rough overview about how many steps our program has to process for just guessing by trial and error. And that is exactly what we're going to do. We will use the brute force approach, which is just trial and error in a systematic way. So we're going to test every possible symbol permutation until we found a match. And I have made a draft here so it is a bit more clear. It will look like this. For example, when we got 5 symbols, we will start with the first symbol at every position. So position 0 to 4, it's all A. And then we test if that is the correct password. No, okay. Then we test the next symbol at the last location. And that goes for all lowercase letters. Then we do that for uppercase and for digits. And then if we reach the last possible symbol at the last position, we start all over again, but this time by also using the next symbol for our previous location. So as you can see here, we go back to A at the last position, but this time, of course, since we already tested all A's, we also bump to the next symbol at the previous location. And then that's the same basically. So these are 62 tests here. These are 62 tests. And again and so on. And we move forward in the positions until we found the password. So depending on how the password actually look like, it might be a bit earlier or later, but the worst case is that we need all 916 and a few steps. So it has exponential time complexity. We already talked a bit about efficient and less efficient algorithms and data structures in previous tutorials. Exponentially is usually very inefficient. That is why we are using a reasonably short password here, and why you should use a long password with lots of potential symbols in practice to make it harder to guess. Okay, let's go back to our program. And the first thing we need to do is we need to actually generate the set of potential symbols here. So we know which symbols to try. And in order to do that, we need to talk shortly about Unicode. So Unicode is a modern and very popular and mature and spread way to represent symbols. Each symbol is represented by a so-called code point. And there is a basic table down here, somewhere here. So let's see. It's not on this page. Basic Latin Unicode block. But it's this, right? So Unicode can represent all kinds of symbols, even non-Latin ones, but we will just use the basics like digits and Western alphanumerical characters. So in order to use these, we have to know what the actual code point is for a symbol. So you can look that up in the internet. And for these well-known ones here, we can see that digits 0 to 9, they got these Unicode code points, that is hexadecimal byte representation, or in decimal it looks a bit different. But that is how you can define them. So the same goes for uppercase and lowercase letters. And now we just have to make sure that we actually create a slice which contains all runes or all symbols that we want to try. So unicode table, we're going to search for another unicode table, and list of unicode characters is probably good enough. And again, here you can see the characters, and they are grouped here by specific meanings. And here is basic Latin. And we got, for example, for the digits, the Unicode code point. That is something that you can enter in your program. And there's also the decimal representation and octal, but we're just going to use the decimal because that's easy to iterate over. So let's start with lowercase characters. And these start at decimal 97 up to 120. So let's write a function that is called symbols, and it will returns a slice of all usable symbols, which is a rune type in Golang. But I'm going to call it symbol here in order to avoid conflicts with the rune type name. So we are going to return a slice of rune. Now first let's make our result slice. That is symbols. I use make to create a slice of runes. Let's say initial size is 0. We're just going to append. It's just called 1, so that is totally fine in terms of performance. Now we're going to iterate from the first decimal representation of a small a, 97, until, but including, so I'm going to use less than equals, the small z, which is 120. And we're going to append to symbols the index value. And as you can see here, cannot use type int as rune. But as I said, rune is just an alias for an int, 32-bit, so 4-byte. So we can simply say convert it to a rune. And we're going to repeat that for uppercase characters and digits. So I'm going to copy this loop here. And now we just have to look up the decimal representations of this Unicode code points. So for capital letters, it is 65 to 90. And for digits, it is 48 to 57. And I'll maybe make a little comment here to immediately see what this is. Oh, these are the lowercase letters. These are the uppercase letters. The digits. So now we can return that, and when we print it for testing, we should see that these are our potential symbols. So let's print them here. And as you know from one of my earlier tutorials, we should make sure that we actually close this file in the end, and we can schedule that with defer. It's just something I forgot earlier. Like this. Dot closer, it's a method. Okay, so let's see if the printing of our symbols works. Yeah, so it seems like these are the symbols, but we actually print the integer values, so 4 bytes each. So these are the representations that we added, and it's just that. It's the unicode code point starting at 97. That's what we did, and ending at 57. Yeah. But now to make it a bit more readable, we can interpret these as Unicode symbols. And here you can see, actually there's the new line missing. You can see our complete set of potential characters. All right. Now let's remove the printing of our red password because we want to guess it. And now we got the symbol set, as you might say. So next we can have a closer look at how to implement the actual password guessing. So in order to understand how our algorithm works, we need to have another look at the general concept. As you can see here, this is the basic schema of how we test for matches. So it's a very systematic approach, and we start with the last position, try every possible symbol at the last position, and then we go back to the previous position, bump the next symbol there, and start all over at the last one. We do that until we find a match or tried everything, but in theory, at least the last try should result in a match. So as you can see here, the symbol bumping moves to the left to the earlier positions after a while. So what we are going to use for that is a recursive algorithm. But before we do that, let's actually build a naive implementation first. And therefore, I'm going to create a new function that will be guess. We're going to guess the password. We need to pass the slice of potential symbols, so we know what to test for. And we need to pass the actual password for testing. And let's see if that is enough. So we're going to call guess here, pass the symbols, and pass the password. Note that we consciously decided to just implement a matches method on password, so we can just check if our match is actually correct. We didn't add anything else, since we don't want to just take the password from the read-in, but we want to actually guess. So now we said that our length is 5. So let's create a constant for that. I'm going to call this length, which is 5, or maybe PV length, so it's a little bit more clear. So now we know we need 5 symbols. We need to choose 5 of them. So a naive approach would be to just nest 5 loops inside, because we need to loop over all potential symbols. And that is exactly this exponentiation, where we use 5 nested loops. So that would look like this. We create a guess slice, which is a slice of runes. We know that the size needs to be 5. It needs to hold 5 symbols, so make it big enough. And now, a bit ugly, but it's a first approach. We can say range over all symbols. I'm going to call it symbol 0. And then, so this is for the first position, index 0. Then we repeat that for every position. So symbol 1, symbol 2, symbol 3, symbol 4. And inside here, well, basically in every for loop, we have to set the appropriate symbol at the position. So this is basically index 0, because we're inside the first loop. And the same goes for the others, just with a different index and variable name. So position 1, 2, 3, 4. And of course the running symbol variable from the loop. So when we went down to the 4th position, so our length is 5, we can actually test. So we run pv.matches, pass the guess. And if that returns true, we know we found it. So we can print found. And then we know we're done, so we can return from the whole function, don't need to iterate further. You can already see, since these are 5 nested for loops, it's hard to read, and you can already see how costly this is in terms of steps required. So time efficiency, as I said, exponential is pretty hard, but for modern computers, 5 levels, it's still pretty doable when we think about 62 symbols. So just for completeness sake, in case we did a mistake In case we don't exit with return, we were just going to print something like miss, or let's say not found. So we know that we didn't get it. So let's see if this actually works, or if we need to fix some bug. Call go run. And as you can see, it works. So we found P8 GX1. Let's see. Yeah, it's that. 0G KAI EP4ND. Yeah, so that matches, and it was pretty fast still. To make it a bit more interesting, let's measure the time it takes. So for that we can use the time package, and we can say now. Gives us a current timestamp. I'm going to call it before and after. Let's actually move it so it's around the guess call, and then we will print and braces the parentheses took this amount of time, and now we need to subtract, so get the duration, which is after minus subtract before, which gives us a duration. Again, the documentation is our friend here in case we are unsure on how to use that. So let's rerun it. Yeah, there's a bit of a, forgot the new line. So let's repeat that. There you can see this took about 436 milliseconds, and the other over a second, and then again milliseconds. So still pretty fast, right? But again, since this scales exponentially, the more symbols you add, like for example special characters, and especially the longer your password is, the more permutations we get, the more test steps we need, and the more expensive it is. So just to give you a general idea. So back to our implementation, this is pretty hard to read and maintain, right? And if we wanted to change the size now, so let's say we want to increase to, for example, 6 symbols, password length 6, to test how long that takes, we have to add another loop here. So we actually have to modify the source code, and it gets even harder to read and maintain, and it's easy to make a mistake. So of course, there are better ways to write this. So this is our naive nested loop algorithm. And one way that is pretty well readable and short and elegant is to use recursion in this case. Now, what is recursion? It is basically just a fancy way of saying that a function calls itself at some point. So it's another form of nesting. These are nested loops, but you can also call the same function that you're actually running, and that leads to a nested call chain called recursion. Now, because this is naturally not that easy to understand, I created a little overview here. So what does our general logic look like? Well, we basically start at position 0 in the password testing. Then we need to check, are we at the last position? So is our guess complete? Can we test? And of course, at the beginning, this is not the case. You can see that here we start without any symbols, and then we add the first symbol, the second, and so on. And only when we are at the length of 5, it actually makes sense to test it against our password. So as long as that is not the case, we go into the no branch here and we pick the next symbol and go to the next position. And then we're going to repeat at C2. So C2 is actually our point where we go into the recursion. Once we have a guess that is long enough, as you can see here, we can actually start testing. So when we're at 5As, we try to match the password. If it actually works out, great, we are done. This is our exit point. It's important to have an exit point when using recursion, because otherwise it's like an infinite loop and it will crash with an error because of a stack overflow, to be precise. Usually it will not match, and that means we need to continue. We check if there are more symbols to try at the current position. So here it is complete, but it doesn't match our test. We got more symbols at the last position, so we go on with the next symbol at the last position, which is B. Then we test again, it is no match, we test with C, and so on and so on and so on. So we actually say pick next symbol, repeat C2. This is when we again recall the function, make a new function call to the same function, so the recursion goes deeper down. Then at some point we reach the last possible symbol at the last position. This is here our 9 because we got the digits last, and 9 is the last symbol in our symbol slice of runes. So then if we still got no match, we actually need to go a step backward. So we say, all right, we tested this, go to the previous position. So basically at index 3 and bump the symbol there. So pick the next one. Like now we go to B at the 4th position, index 3. And then we start all over again at the last position, starting with the first symbol, A, B, and so on, until we reach the 9. We test. If it doesn't match, we continue with the next symbol, make a step backward to the previous position if we tried every symbol. And at some point, we will find a match like this here. So the overall concept is start at position 0, add first symbols if you are not yet at the length where a guess makes sense. And once we have this length, so 4As for example, test. If the match matches, we are completely done. Great, exit the recursion. If not, then for more symbols, try again, pick next symbol at the current position, which is the last one in this case. And repeat the function. If not, we need to go a step backwards and actually pick the next symbol at the previous position. And again, here it is marked with color. On these locations, we just call the function again because the whole process repeats. And by using this recursive approach, we don't need to add or remove loops, which become very hard to maintain and read. So I hope that is a bit clear now. If not, don't worry too much. It will get more natural the more often you apply this concept. And what helps is that we actually implement this now. So instead of using this nested loop approach, we will write another guess. I'm going to, we can just remove that. And now instead of writing loops, we're going to call guess recursive. And what do we need for that? Let's write the function first. So guess recursive. Of course, we need the slice of potential symbols. We also need the password for testing. And what else do we need? The current guess, which is the slice of runes size 5. And we need to know at which position we are. So let's call this just index, which is an int. So we are going to pass this here. So these are just the symbols. Let's call this symbols. And the password. And our current guess slice. And what is the index that we start at? Of course, it is 0 as shown in our concept overview. So now how does the recursive implementation look like? Well, we can pretty much look at our concept. First, we have to say, is our guess complete? So check if guess has sufficient length for testing. And we can see that by looking at the index. So if our index has at least the size of the expected password, which is PV length, then the time is right for testing. So we can say pv.matches guess. So, and if that returns true, we are done. And that is the exit point of the recursion, which you should have in every case. Otherwise, you will get an endless loop or a Stack Overflow error, to be specific. So in this case, we can say found it. And we will return, because otherwise we are not really exiting. Now, next, we need to actually iterate the symbols. So let's say we are not yet. Actually, let's return here too. We need to do that because otherwise it will continue at an index which is large enough for testing. So let's say this is not the case. Actually, we can also write it with an else. Let's do this first. Then we need to make sure that we test the next symbols. So we can do that by iterating over the symbols that we know of. And we know at which index we are, so we can actually set the symbol there. So guess at index position is assigned the symbol. And now our recursion comes into play. So when you look here, you can see that pick next symbol. And we repeat at the function entry. So we can just call guess recursive. we need to pass these symbols because they are still needed with password, our current guess, and the index. Now the important part is we need to increase the index here. So we are actually in this branch here. We need to go to the next position, and we do this by ensuring that we pass the next index, which is index +1. And that is it. So to quickly recap this, we are starting with the first position, index 0, and basically an empty guess rune slice. So the default value is 0 in all elements. Once we reached a sufficient length, so we test that with our index, we can try to match our guess against the password. If we found it, we need to return. So it makes sense to actually communicate if we should continue our recursive dive or not. So we have to specify a Boolean return value. We're going to use a Boolean here. And we say true if we want to abort, so if we found it. And then we can check that here. So if guess recursive, if that returns true, then we also want to return true here in order to abort. Because otherwise we would continue the loop with the next symbol and we wouldn't really abort. So that is required. As long as it's false, we continue with the next symbol and so on. So that is actually our exit. So here we can exit without a return value, but you know that it will continue in the previous call where we called it recursively, and there it would continue with the for loop, even though our inner guess exited. That is not so easy to understand, but you will get used to it the more you use recursion and the more you think about it and try it yourself. So finally we have to define a return value here. So we would come here when there is no match, or we tried every symbol. So in this case, we don't want to abort completely, but we return false, so it continues further. It goes one stage up in the recursive call chain, and then for the previous position, it will try the next, and so on. So this is actually signal that could not find match yet. Continue with next symbol at previous position. So that is our basic structure. So let's compare this to our little diagram here. We start at position 0, that is here. We check if the guess is complete, that is this location. If yes, we can guess if the password matches. If it does, we are completely done and we're exiting with true. It's important to check this here when we recall the function recursively to actually exit there too, because it's nesting down in the call chain. If not, we check if there are more symbols to try at the current position. So we basically do this with our for loop, just runs until we tried every symbol. Finally, if we tried every symbol, we just return false, which means continue one call chain up higher and try the next symbol with the previous position. So that is then this case here. All right, let's see if this actually works. So if we made a mistake, guess we'll call guess recursive, and it should exit at some point. Otherwise, we get a stack overflow error, and it will print the time it takes. Oh, so it actually said not found, but we found it. So there's a small bug in there. That's because we printed here not found. That is no longer correct. So instead, we would say if here at the first recursive call, if this returns false in the end, so every possible permutation has been tried, but it still returns false, then we got not found. So that was a small bug. Let's try again. And you can see it works. It takes a bit longer than our first naive approach. Well, let's see, how long did that take? 400 milliseconds, 1 second, and 400. So roughly speaking, it's about a factor of 3, I would say. It takes 3 times as long, so there's a decent performance price to pay, because in recursion, the program actually has to make sure that a lot of nested recursive function calls happens. So it has to remember the old location, you know, when we go back to the previous position, it has to remember the stack, which is the variables in the parent function scope, because it is not done. So when we call it here, the program still has to remember this first part, like the variables and the instruction pointer where we were and so on. Then it steps down, and when this returns here, we are back in the upper parent call, and that needs to be tracked. So that is a little performance overhead for recursion. That's the price we pay here, but it is much easier to read and maintain because it works for basically all kind of lengths, and we can test that. Let's go down to 4 places. This will be a bit faster, so I'm going to delete one symbol here, just change it to 4, and it's very fast because it, let's see how much it requires. It requires only 14 million tries in a worst case scenario instead of 916 million and a few. So you can see it's definitely in the millisecond range here. And the other way around, we could add 2 places. This will take quite a while. So let's see. Just going to add a few here. Like this. And bump our length to 6. We actually made a mistake. So here's index out of range. That is because we still got a hard-coded length here, another bug. So as you can see, not writing unit tests for that is pretty buggy. So we have to test it manually because we want to focus on the algorithm here. But we found it, so this needs to be the password length. So we only have to change that and our example passwords. So let's try again. And it runs, and it will probably take a while because we are now at, let's see, whoa, this is 56 billion. So that is quite a lot. It will probably not complete in a reasonable amount of time. But in theory, you should be able to reuse that for any length if you got enough computation power or enough time on your hands. So that's it. That's our recursion example. This is a fundamental point for our next tutorial videos. So there are quite a few things that we can improve. We already talked about performance and efficiency. And one example is we can make use of concurrency in Golang. So concurrency is something that the Golang developers thought a lot about. And there's quite a few nice things that we can use to utilize modern CPU architectures. So you probably have more than one CPU core, even if your computer is not high-end. Mine certainly is not, or no longer. But right now we're just using a single core. So you can see it took 1.5 minutes for the first. And when I look at my CPU load, I can see that mainly puts pressure on one CPU node. So that is our Golang program here. And I sorted, I can see that it's the password tester. The rest is the recording program mainly. So this is just serial implementation. And we could make use of multiple CPU cores by making this a bit more concurrent in the implementation. That is a future topic that we will talk about. Of course, as always, I recommend that you read about it, test it yourself, maybe pick a project for yourself or some educational material in order to get the practice and actually understand it. So it might be you didn't quite get how recursion works. That is fine. Just make sure that you work on it and you get some practice under your belt to understand it better. I hope it has become a bit clear and you got a starting point for that. I hope you liked it. Feel free to leave me feedback, give a thumbs up if you liked it. If you didn't like it, tell me what you want me to do different, and also what you want me to talk about in the future. See you next time.